So welcome to the final review for calculus. This is going to be a three-part series. The first one's going to cover chapters 1 to 3. The second part's going to cover chapters 4 and 5. And the third part's going to cover chapters 6 and 7. And the reason why we're splitting it down into separate chapters is because now AB students only have to watch the first 2 videos, while BC students have to watch all 3 because they learned about concepts in all 3 videos. Now AB doesn't unnecessarily have to watch stuff that they didn't learn from a longer video, and this is shorter, more bite-sized content. Although these videos are probably also going to end up around 30 to 40 minutes long each. So it is a lot of content that we're trying to pack into 3 videos. But without further ado, let's get started. Chapter 1 is basically reviewing pre-calculus and introducing calculus. Some basic stuff to review, like the equation of a line. Y is equal to mx plus b. That's a slope-intercept form of a line, because we're given the slope, m, and the y-intercept, b. And slope formula, also something you should probably know if you're taking calculus. It's going to be the change in y over the change in x. And it determines basically the steepness of the graph. And it's actually a big concept in calculus, which is why I'm actually reviewing it. The slope of a function is found by its derivative. But since we're focusing on lines right now, the slope is just simply change in y over change in x. And finally, one more form for the equation of a line. Y is equal to m times x minus h plus k, where m is the slope and h comma k is a point on the line. And this is actually used more often in calculus because the main reason we're using lines in calculus is because of tangent lines to a curve. We're given the slope from the derivative, and we're given the point because that's the point it's tangent at. So since we know the point and the slope, we use slope form. Now, that's lines, pretty basic. But now we're going to escalate a lot and talk about continuity. Continuity, we're talking about the informal definition of continuity right now because the formal definition requires limits, which is not in this chapter. What we're basically going to be talking about then is the informal definition, basically saying if a function can be drawn without lifting up your pencil, it's continuous. This, I can draw it. I didn't have to lift up my pencil, or in this case, trackpad, and therefore it's continuous. What about this, though? As you can see, I had to lift up my finger and or pencil, and then I had to draw 2 separate parts on the graph. Therefore, it is not continuous. Basic rule, piecewise defined functions need to be connected to be continuous. So you can have something that's like this, and then dramatically switches into this, but it's still continuous because I didn't have to lift anything up. And basic rule of thumb, polynomial functions, rational functions, power functions, exponential functions, logarithmic functions, and trigonometric functions are all continuous at all points in their domain. That's just a general rule of thumb. There are exceptions. Rational functions are not always continuous, and that's why I pointed out all points in their domain, because this can be a rational function. Technically, it's not defined there, meaning it's fine if it's not continuous there because that's not continuous at a point in its domain. It's not in its domain, so it still upholds what I just said. But you need to be careful when it comes to rational functions, since they're the most common culprits of discontinuities, along with piecewise functions. Now, speaking of domain, we have to review domain and range of functions, which again is algebra, but good to know. Domain is basically the set of x values that it can be. The range is the set of y values it can be. And there are 2 ways you can represent that. Inequality notation, which is probably what you used in algebra, or at least the beginning part of algebra, using less than, greater than, less than or equal to, greater than or equal to, and not equal to. That's basically like the basic symbols for equalities and inequalities. And what you can do here is you can say something like x is greater than 0. That is the domain of the function. Now, how would you translate that into the other type of notation, which is interval notation? Interval notation uses brackets and parentheses, and then the other type of brackets and parentheses, or the other end. And what the rule basically is, if it's inclusive, you use square brackets. If it's exclusive, you use parentheses. In this case, x is greater than 0. So that's going to be exclusive since x cannot be equal to 0. So you have a parentheses, 0. And then since it's greater than, you just go all the way to infinity. So you write an infinity. And then what do you put after that? Parentheses or square bracket. Whenever you see an infinity, you put parentheses because you can never be equal to infinity. So there's no point in putting a square bracket since it can never be equal to that. Another example would be x is greater than or equal to 0, in which case you would remove this parentheses and turn it into a square bracket. And this is basically the same thing. You can write x belongs to show that this is representing domain and not range. But usually you can write domain and then this. Usually we're going to be using this in calculus. I wouldn't suggest using this since that's more algebra. That's probably what you would use in algebra. In calculus, we were talking about the next level, so we talk about interval notation. Fun. Moving on to our next topic. This entire chapter is just going to be like a combination of random review topics. So moving on is polynomial division. Polynomial division, we have two polynomials and you're basically dividing them. That is pretty self-explanatory, but you have something like x cubed minus 6x plus 5, right? And you're dividing by x minus 1. I'm going to show you this example because that's probably the best way to learn polynomial division, although this is just a review of polynomial division. There's not really any like theory you learn, it's just practice. You should know how to do it and you can do it for anything. So let's do this. X minus 1, you look at the x and you look at the x cubed, it goes in x squared times. So you basically multiply this by x squared to get x cubed. So now x times x squared is x cubed. This is just like regular division, by the way. If you have like 6 and then you have 71, you look at 7, you look at 1. How many times does 6 go into 7? 1 time. So you do 6 times 1 is 6, and then you subtract and so on. That's basically what we're doing here, but with polynomials. So it's a bit more advanced. Now, we have x times x squared was x cubed. Then negative 1 times x squared is negative x squared. So you minus x squared. Now the x cubed cancels out. And note that we have a 0x squared, an imaginary ghost 0x squared over here. So you do 0x squared minus 1x squared, and you get negative 1x squared. You bring down the minus 6x, and you repeat the process. How many times does x go into negative x squared? It goes negative x times. And if you do this enough times, it'll just become secondhand nature. You don't really have to think about it. So you do negative x times x is negative x squared, as expected. We do negative x times negative 1 is plus x. And you subtract, these cancel out. Negative 6x minus x gives us negative 7x. And then you bring down the 5. Finally, how many times does x go into negative 7x? Minus 7 times. So you multiply that, you get negative 7x. And then negative 1 times negative 7 gives you plus 7. Subtract, they cancel out, no surprise there. 5 minus 7 gives you negative 2, and that's your answer. But what do we do with the negative 2? So this is the main part of the review. What do we do with that remainder? In regular number division, you would say something like 11 remainder 5. That would be the answer to this, by the way. Sorry for spoiling it, but 11 remainder 5. We can't really do that here. We can't write x squared minus x minus 7 remainder negative 2. Instead, we write x squared minus x minus 7. And then we put a negative 2 over our the number we're dividing by. So it's x minus 1. So you write plus negative 2 over x minus 1. Because basically what this is saying is the negative 2 didn't fully go into the x minus 1. That's why it's a remainder. So we're keeping it apart. Same thing you can do with numbers, actually. You write 11, and then you write, oh, but there's that 5 that didn't really go into the 6. So 11 and 5, 6. Then that just becomes a mixed number after a while. The short form for which is 11 and 5, 6, the mixed number. So another thing you could do is, since it's plus negative 2, you can just write a minus 2 over x minus 1. If you keep the plus, that's an added bonus because it shows that it's a remainder. With the minus, it could get a bit confusing because it doesn't really make sense why you would do a minus. Like you won't ever write 11 minus 5 over 6 because that's the remainder. But no matter, it's polynomials. And then there's the area model method, which I'm not going to go over because you only need to know one method to divide polynomials. If you want to do the area model method, that's your choice. I just prefer long division since it's much easier to understand, in my opinion. Area model is also useful, but this is very close to regular division, which is why I'm talking about that. Now, moving on, we talked about polynomial functions with this. We are going to move on to rational functions with asymptotes. We're going to be talking about asymptotes. And again, we're talking about the informal asymptotes because formal requires limits, like I said, similar to continuity. So the horizontal asymptote is when the function approaches a horizontal line as x approaches either positive infinity or negative infinity, or both. So if you have the regular rational function, this, fun fact, this is actually called the reciprocal function since it's just 1 over x. If it's like 1 over x plus 1, it's no longer called the reciprocal function. It's called the rational function, but, you know, fun fact. So the horizontal asymptote here is going to be y equals 0 because as x approaches infinity, y is going to be getting closer and closer to the x-axis, which is the line y equals 0. Now, I talk about approaches. That's limits, which we're actually going to be covering next chapter. But this is the informal definition, like I said. There's one more thing, slant asymptotes, which you might or might not have covered in pre-calculus. I'm not really sure, but you're definitely going to cover it in calculus, that's for sure. So a slant asymptote is basically a line that, like the equation of a line that the function approaches. So it could look something like this. And obviously there's a vertical asymptote here, which we didn't talk about. This section is mainly about horizontal asymptotes and slant asymptotes, but there's always going to be vertical asymptotes in some cases. And that's basically when the denominator equals 0. Again, more on this later when we're talking about limits and everything. We'll go more in depth into it. But there's usually a vertical and horizontal asymptote or a vertical slant asymptote or combination of them. In calculus, we'll be learning how to find the equation of the slant asymptote. That really has to do with what we just learned about polynomial division. So just foreshadowing a little bit. Final thing about asymptotes, horizontal and slant asymptotes can actually be crossed, while vertical asymptotes can never be crossed. Good rule of thumb, you don't usually see horizontal asymptotes being crossed unless it's a really weird function like this, where it is approaching 0, but then it crosses it and then comes back up. So this is like a bad drawing of it, but sometimes like the middle section is here in the middle, and then it basically goes under the x-axis and then back on top to go towards infinity, which is crossing the horizontal asymptote, since the horizontal asymptote would still be y equals 0 in this case. But yeah, it can be crossed. Vertical asymptotes cannot be crossed. Now, we're going to be talking about approach statements. Like I said, this is a complete random mixture of pre-calculus algebra topics that are just put together in one chapter to try to learn and review as much as you can. So approach statements, think of it as like a precursor to limit statements or limits. It's like a less powerful, but still does the same kind of thing. And the reason why I'm saying it's less powerful is because limits are very easy to read and easy to write, and they're very concise. Approach statements, approach statements basically say as x approaches 0, y approaches 2. That is a very long way to write a limit. And we'll talk about limits in chapter 2, like I've said probably 10 times before. But these approach statements are useful before we learn limits because it basically does the same thing as a limit, except it's just a sentence describing it. It's usually used for end behaviors and asymptotes and sometimes even holes, just the same applications that limits are usually used for. Again, random topics, but we're going to move on to functions, specifically inverse functions. You have a function f of x. The inverse of it is f and then a little negative one up there. That doesn't mean 1 over, because usually when you write like 2 to the power of -1, that's 1 over 2. That's not what's happening over here. It's the inverse, not the reciprocal. So the definition of it is when you take the composition of functions of a function and its inverse, you're going to get x. And this is the same when you switch the order as well. If you do the inverse function on the outside and the original function on the inside, you're going to still get x. Sometimes there's domain restrictions, especially when you're dealing with square roots and stuff like that. If you have the original function be x squared, and the inverse, therefore, square root of x, since the square root is the inverse of the square, you're going to need to restrict the domain of the original function to match this. Quick example of what I mean. This is x squared. It's both sides, but square root of x is only this side. So you need to restrict this domain of x squared to be only this part of the graph and ignore this part, because otherwise the inverse won't be a function since it fails the vertical line test. Another key point about inverse functions is that to find the inverse on a graph, it's just the reflection across the line y equals x. And that has something to do with calculus. The entire reason we're reviewing this now is because in probably few more chapters way ahead, you're going to be learning about stuff to do with inverse functions in calculus. So that's why we're reviewing everything. It may seem like a random mixture, but they all matter in the end. Now moving on to even and odd functions. So we talked about inverse functions. Even and odd functions are basically also have to do with symmetry, kind of. Even functions are symmetric around the y-axis. So x squared is a perfect example of an even function because it's symmetric across the y-axis. And then there's odd functions which are symmetric about the origin. X cubed is a perfect example because if you rotate it 180 degrees, you're going to end up with the same function, which is basically the definition of odd functions. Even functions satisfy the condition f of negative x is equal to f of x itself. So when you plug in an x value that's on the negative side, it's going to be equal to the same x value on the positive side. It'll be the exact same. Odd functions, on the other hand, f of negative x is equal to negative f of x. So when you plug in something on the negative side, it's going to be, the y value is going to be the negative of the same point on the positive side. So f of 2 is going to be 8, let's say, because it's x cubed. F of negative 2 is going to be negative 8 because it's the same y value except negative. We're coming to an end right now for chapter 1. Just a few more topics that we need to cover. Finite differences. So if you have like a sequence or a function, like 1, 3, 5, 7, 9, that's a sequence. Finite differences are the change in values. So this is going to be 2, 2, 2, 2. That's what makes it arithmetic. You can do that with functions too. And that has a lot to do with the slope. The official definition of finite differences is change in y values between consecutive x values. If you have a linear function, the finite difference is basically going to be the slope. So it has a lot to do with slope, which is why we're covering it. And general rule of thumb, functions in the same family have similar finite differences. So not the exact same, because y is equal to 2x has a different finite difference than y is equal to 5x. But they both have a constant finite difference. That's what I mean by when I say they have similar finite differences. If you have y equals x squared, that does not have constant finite differences, making it different than y equals x. And moving on, we have trigonometry. This is pretty important, especially as we get into some more derivatives and integrals, because you're going to need these identities to simplify a bunch of stuff in the future. The main identities you need to know are reciprocal identities. So secant of theta is equal to 1 over cosine of theta. And I'm assuming you know the basics of trigonometry, like sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent, and so on. Since you've probably covered that in pre-calculus, geometry, and algebra. Cosecant theta is going to be 1 over sine theta. And then tangent theta is going to be sine over cosine. So the reason why that's the case is because sine is opposite over hypotenuse, cosine is adjacent over hypotenuse. The hypotenuses cancel out and you get opposite over adjacent, which is the definition of tangent. Finally, last, reciprocal identity, cotangent of theta is going to be cosine over sine. And you can use this to prove that cotangent is actually going to be 1 over tangent, which is yet another reciprocal identity, but that's pretty much connected with these, so you don't really need to know that separately. A few more important trigonometric identities. Pythagorean identity. I'm just going to show you sine squared theta plus cosine squared theta is equal to 1. There are 2 more, namely tangent squared theta plus 1 is equal to secant squared theta, and 1 plus cotangent squared theta is equal to cosecant squared theta. And I'm not going to write them on the board over here because you can easily derive them with this. And then that's basically the majority you need to know. There's just double angle sine of 2 theta is equal to 2 sine theta cosine theta. This could be useful when we're talking about calculus. And then there's cosine 2 theta. This is less common, and since there are 3 varieties, I'm only going to write 1. It's going to be cosine squared theta minus sine squared theta. And like I said, there are 3 variations of this. You can use any one of them you wish, but this is the one I'm going to write down since it's pretty simple. 2 last sections in chapter 1, and chapter 1 is probably the longest one of this since it's reviewing a bunch of stuff, but some basic physics stuff. Position is where an object is. So initial position is at initial time. Final position is at final time. Displacement is the change in position over change in position of that object, and distance is the total amount of the object's motion. So let me show you why they're different. Let's say an object started here and ended here. What's the displacement? Just the change in positions. Easy. Now let's say the object started here and ended here, but actually went all the way around here, made a pit stop here, went all the way here, then came back here, and then still continued on and made it there. The distance, total amount of change in position. So at every interval, basically, you take a change in position. That's not really the way you think about it. It's the total amount of motion that it went through. Displacement still is the same exact displacement. So that's why displacement is kind of not, it doesn't really give you the full picture, because let's say you go in a circle, you definitely moved, but your displacement is 0 since you ended up in the same position. So take displacement with a grain of salt, but that's mostly what you use in physics, because they're not going to throw some curveball at you where the displacement is 0 and they're asking you to find something. But usually that's not the case. And finally, some more stuff about motion. We've got velocity, which is the rate of change of position. So it's going to be the change in position over change in time. And as we get into calculus, we're going to talk about a more calculus way of thinking about velocity. So the velocity is positive when an object is moving forward, negative when it's moving backwards, and 0 when it's not moving. The speed, on the other hand, which doesn't really have a symbol to denote it, so I'm just going to write speed. That's going to be the absolute value of velocity. Because speed is always positive since it's distance over time rather than displacement over time. Distance is usually going to be the positive version of displacement. Like I said, there are some cases where it's not the case, but they're not going to make a problem that difficult for you, most likely. Acceleration is going to be the change in velocity over change in time, or the rate of change in velocity, basically. Again, it's positive when the object's speeding up, negative when it's slowing down, and 0 when it's at constant velocity. The average velocity is going to be equal to, like I said, the displacement over total time. And the symbol for that is this bar over the v. The reason why the actual velocity is not that is because of calculus. So we're going to get into instantaneous velocity, or at an instant, what is velocity, a bit later. But that's all for chapter 1. Moving on to chapter 2. Chapter 2 is where we actually get into calculus stuff. So exciting, I know. We've got the trapezoid rule and summation notation. Those are the things we're starting with. And as you can imagine, that means we're starting with area under the curve. This is, again, sort of a review of pre-calculus, since you probably should have talked about this in pre-calculus. But the trapezoid rule basically says, if you have a curve and you want to approximate the area using trapezoids, which is actually a pretty good method for approximating area, the area is going to be the width divided by 2 times the value of the function at the first point plus 2 times the value of the function at the first point plus the width. Same pattern all around until we get into 2 times the value of the function at the last point minus the width, plus the value of the function at the last point. So this is a very complicated way of basically saying, take the height here, you take this height here and multiply by 2, this height here multiplied by 2, this multiplied by 2, and then you take the last one and just multiply it by 1, add all that together, multiply that by the width, and then divide by 2. That's the trapezoid rule. That's a very good approximation of area, usually, unless you have something like this, and then you only have one trapezoid, in which case it's a very bad approximation of area. But, you know, in most cases, if you have a lot of trapezoids, it's a good way to measure. So now we're going to get into other ways to measure approximate area. But before we do that, we have to talk about summation notation. So sigma, this summation symbol, is used for the sum of a lot of numbers. So we have summation from k equals 0 to n. In this case, let's say 5 is the final term, and it's going to be k squared. So this is the index or dummy variable. This is the argument, and this is the final position, initial position. So how you would calculate this is plug in 0, you get 0 squared is 0. Then you go to the next integer, you plug in 1, 1 squared is 1. Next is 2, 2 squared is 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. And then you stop, because 5 is the last number, meaning we don't go past that. So this is going to be what you end up calculating. 0 plus 1 is 1, plus 4 is 5. Plus 9 is 14, plus 16 is 30, plus 25 is 55. And that would be your answer for this problem. So now we can finally get into the other ways to calculate area, namely LRAM, RRAM, and MRAM. LRAM is left endpoint rectangle area method. And it's basically going to be from k equals 0 to n minus 1. So the left endpoint. So that's this endpoint, which is why we're going from 0 to n minus 1. It's always the left point of each rectangle. And it's going to be the width times f of a, the starting position, plus the width times k. Looks complicated, but you really only need to memorize one of these formulas, really, because the others follow a very similar pattern. The next one is k equals 1 to n. Instead of 0 to n minus 1, it's 1 to n. So you're looking at the right endpoints here, which is why you're starting from 1 rather than 0. And it's going to be the exact same argument. The width times the value of the function at that point. And finally, we have midpoint, which definitely does look a bit different, but I'm going to show you a little shortcut. It's k equals 0.5 to n minus 0.5. And you can do this on calculators. It's not best practice, but honestly, I think it should work. If you were to write on paper, obviously, you would not use this method, because the upside is that you use the same argument, so you don't have to memorize anything new. The downside is that it's not really best practice for math, and you might get in trouble. But I can't really write all 3 different all the different variations for each one on the board. So I'm just going to show you the simplest one for each one, and then you can try to derive the other formulas. Okay, we're finally done with area. Now we just have to talk about limits, continuity, and some other stuff. Limits. Basically, limit is the value of a function as it approaches a given number. So limit of x as x approaches a of f of x basically says this function f of x, when x is near the value a, what is the value of f? So for most functions, it's pretty simple. A is this point. So you look at the surrounding areas, what does it approach on both sides? And then you get your answer. I kind of spoiled it a bit there. What does it approach on both sides? You're going to take the one-sided limit for both sides. So the plus indicates from the right side. And then the minus indicates the left side. And you're going to set these equal to each other. Because if they are equal to each other, then the limit at that point exists. If it doesn't exist. Simple as that. Note that the limit as x approaches a of f of x does not have to equal the actual function value at f of x. Here's a pretty common example. You have a hole here, and then you have another point above that or below that that has the actual value of the function, but it's not equal to the limit, since near it, it's approaching this point, not the actual value of the function. So they're not the same in this case. So now that we know limits, we can talk about continuity. A graph is continuous if, like we said, you can graph it without lifting your pencil, but there's a three-step definition of continuity. First of all, the limit as x approaches a of f of x exists. In other words, do both one-sided limits exist, and do they equal each other? Check if that's true. The second one is f of a exists. So make sure the actual function has a point there. Otherwise, there's a hole, meaning it's not continuous. And the third one is make sure that the limit as x approaches a of f of x equals f of a. So that's a lot to digest, but let me break it down for you. First condition basically checks if there is like a jump discontinuity. That's what's called a jump discontinuity. There's a visible gap between the two parts of the graph. Another possibility for number one is an infinite discontinuity, or basically a vertical asymptote. Both of those are ruled out by number one. If number one is true, then it cannot be either one of those discontinuities. Number two is a hole. It's just a straight up hole. The function does not exist at that point. And the third one is a bit more interesting. It's a hole, but the function still exists at that point. Like I showed you in this example down here, there's a hole, but the function still exists at a different point, not on the graph. So that's continuity for you. Moving on to the intermediate value theorem. So finally, we're getting into some actual calculus with some theorems and stuff. This is not one of the most fun theorems. There are better theorems out there, to be honest. But the intermediate value theorems basically says if there's a function that's continuous over a closed interval, a comma b, closed is important, for every value m, let's say, between f of a and f of b, there exists at least one x value such that f of that x value is m. A lot of words there, but let me explain. You have a function, ab, and it has f of a and f of b. What it's basically saying is as long as the graph is continuous on this closed interval, every point between f of a and f of b, the graph goes through at least once. It can go through it multiple times, like this, but it has to go through them at least once. If it's not continuous, though, it can be something like that, and it doesn't go through these points over here, which is why it has to be continuous. Now, why does it have to be continuous on the closed interval? Take a look at this. I can draw this graph such that it's a straight line, and then there's a hole here, but the function is defined up here. So there's still the interval a, b, but it's continuous on the open interval a, b, not the closed interval. Because at B, it's not continuous. At A, it is, and everywhere in between, it is. So it's closed on this interval. But as you can see, it does not satisfy the intermediate value theorem because there are so many points in here, infinite actually, that the graph does not go through. Meaning, it has to be a closed interval. It cannot be a semi-open or a completely open interval. It has to be a closed interval. Almost done with chapter 2 here. We just have to talk about trig limits and local linearity, which is pretty simple. There's two main limits that you should know. Limit as h approaches 0, and I'm using h here because that's calculus stuff. H is something you use in calculus. So you do sine of h over h. This is going to be equal to 1. You plug it in, you get sine of 0, and you get 0. Then you plug in 0 into the bottom, and you get 0. You get 0 over 0, which does not exist. Meaning, how is it equal to 1? I can't prove it. You technically actually can prove it right now, but that takes too much work. There's something in the future with calculus that we'll learn that helps you show that this is true. And then limit as h approaches 0 of 1 minus cosine h. This looks interesting. Over h equals 0. The reason why this looks interesting is the denominator is still over 0, but numerator is cosine h, and cosine of 0 is 1, which is why it's 1 minus cosine h. So 1 minus 1 is 0. So again, it's 0 over 0. We cannot, just plug it in. Again, calculus stuff, that'll help us prove it, but for now, we don't know. And finally, local linearity. Basically, you can have the most curviest of curves, but if you zoom in far enough, you zoom into this portion right here, if you do it on like a calculator window, it's going to look like a line. So every single curve basically looks linear if you zoom in far enough. So that's something that we'll play on in the future when we're talking about approximating values with tangent lines. That's chapter 2. And I think I can start chapter 3, but I doubt I'll be able to finish chapter 3 in this video since we'll probably get cut off. So we'll probably start talking about derivatives. What is a derivative? Derivatives are basically slope functions for curve. Before we talk about that, though, let's talk about rate of change. The average rate of change over an interval for a function, or AROC, is going to be the f of a plus h minus f of a over h. So that is going to be the average rate of change. So you take a point A and you take a point A plus h. So it's basically h above it. And you find the values of the functions at those points, subtract them, and then you divide by the change in x, which is h. So this is basically the definition of slope. Now, the reason why it looks nice here in theory is because this looks linear. But if we have something like this, where it's from here to here, that is most definitely not, that's not remotely close to what the actual rate of change is. And it actually changes from point to point. So we cannot really use that. IROC, or instantaneous rate of change, though, is more useful because what we can do is we can write limit in front of the AROC. Just the same expression, except we just have a limit. So I'm just going to write AROC here to save some space. But you just plug in this expression into this limit, and you get the instantaneous rate of change at that point in time. How does this have to do with derivatives? The derivative at a point is literally just the instantaneous rate of change at that point. It's the slope of the tangent line at that point. No matter what you call it, it's the same thing. Derivative, slope function, slope of the tangent line, instantaneous rate of change. It's all the same thing. Finite differences, actually. It also has to do with derivatives. Limit definition of derivatives, whatever. They're all the same exact thing. So f prime of a is going to be this same expression. It's going to be IROC. At a point, it's going to be limit as h approaches 0 of f of a plus h minus f of a over h. F prime of x, though. So what's this? And the prime means derivative, by the way. at a point, it's basically going to be the slope of the tangent line at the point. But what does it mean if we take x, just then the domain, basically, f prime of x? So what that's going to be is this entire slope function, which is basically just a function that you can plug in x values and output the derivative, instantaneous rate of change, or the slope of the tangent line at a point. And it's more useful than finding this because that can only be used for that one point. Let's say you want to find the rate of change at both x equals 1 and x equals 3. Better to find the slope function or derivative and then plug in both 1 and 3 later. So this is going to look slightly different. It's going to be limit as h approaches 0 of the same thing, except we replace a with h. So it's going to be f of x plus h minus f of x over h. Why is this useful? Again, we replace it with x to make it more general for all values of x. And yeah, that's the limit definition of the derivative. There are a few rules we can talk about with the derivative. The first one being the power rule. And we're not going to really talk about the other rules right now. They come up later in different chapters. Chapter 5, actually, we're going to be talking about other rules for derivatives. The power rule basically says if you have a function f of x is equal to a times x to the power of n, f prime of x is going to be n times a times x to the power of n minus 1. So what you're basically doing is bringing down the n and then subtracting 1. So let's say we have x to the power of 6, 2x to the power of 6, actually, to make it a bit more complex. You bring down the 6, so 6 times 2 is 12. Now the coefficient becomes 12. And what do you do with the x? You just subtract 1 from 6 and you get 5. 12x to the power of 5 is the derivative of 2x to the power of 6. Now what about 5x? What's the derivative of that? Well, that's going to be just put a 1 there because x to the power of 1 is just x. So you bring down the 1, doesn't do anything to the coefficient. And then you do 1 minus 0, which gives you 1 minus 1, which gives you 0. And x to the power of 0 is just 1. So your answer is going to be 5. This derivative of 5x is just 5. What about 5? What's the derivative of 5? We can just use this then. Again, we write an x to the power of 0 because x to the power of 0 is just 1. We bring down the 0, meaning the coefficient 0. And then 0 minus 1 is negative 1. But the coefficient 0, meaning the entire answer is 0. You cannot go further than that because 0 times anything is 0. What about something like 5 over x? That's just going to be 5x to the power of negative 1. So like with any other expression, we bring down the negative 1. We get negative 5 because negative 1 times 5 is negative 5. And then x to the power of negative 2. And you can write this this negative 2 as a reciprocal, so it'll be negative 5 over x squared. Finally, one more application. What about x to the power of 1/2? We can still use power rule for that. You bring down the 1/2, and you have x to the power of what's 1/2 minus 1? That's going to be negative 1/2. And again, you can write this as both a square root and as something in the denominator to get rid of negative and fractional exponents. But, for the sake of this, you can leave it like this. That's the power rule, very powerful rule, but actually it's not the most powerful rule because there are cases where you cannot use it. What about sine x? How will you differentiate sine x? What about x times sine x? What about x over sine x? There are a lot of things you cannot use this for. A few brief things to mention. When you have the sum of two functions and you take the derivative of that, it's going to be the sum of the derivatives of the two functions. Basically, if I have 5x squared plus x, you basically differentiate each function by itself. Derivative of this is 10x. Derivative of x is 1. So you add them together and you get your answer. Same with subtraction. Not the same with multiplication, though. Multiplication is different. There's something called the product rule, which we'll learn in chapter 5. There are different types of notations for derivatives. we have f prime of x, obviously. That is equal to dy dx or d dx. This is actually called Leibniz notation, using the d's, dy dx, for example. It's up to you, whatever you prefer. There are different applications for both. But what about more than that? This is called the first derivative. What about the second derivative? There's f double prime of x, or f, it's usually just called f double prime of x, or second derivative of x. This is a bit trickier than you might imagine. It's d squared y over dx squared. A bit weird, yes, but makes sense if you actually understand what Leibniz notation means, which I cannot get into now. For the nth derivative, you can just put a parentheses n up here, and most people will know what you're talking about. Again, as you might imagine, in Leibniz notation, it's d to the power of ny over dx to the power of n. Okay. Now, we talked about stuff you can do with derivatives. What about applications of derivatives? There are two main applications, which actually are just one, that we're going to cover. They both are very similar to each other. Curve and function analysis. Curve analysis, basically, you can determine whether a function is increasing, decreasing, concave up, concave down, has a maximum, minimum, or point of inflection at a certain point. Curve analysis and function analysis are actually very similar, so I'm going to cover them both right now. I like to draw a little table. If you have f of x, f prime of x, and then we have f of x, or actually, this is good enough. We have f double prime of x here. We can all fit it in one table. So when f prime of x is positive, f of x is increasing. And when f prime of x is negative, it's decreasing. Now, what about when f prime of x is 0? And there's actually two cases. One is when it changes, and I'm actually going to make it a bit easier to write. I'm going to say it goes from positive to negative. So basically, f prime of x goes from above x-axis to below x-axis. So it crosses 0 in the process. And that's what we're looking at. At that point, what happens? So if it goes from positive to negative, it's going to be a maximum on f of x. And what about negative to positive? As you might imagine, it's going to be a minimum. That's basically all you can do with f prime of x. But there's stuff you can do with f double prime of x. If f double prime of x is positive, you're going to have increasing f prime of x, and you're going to have a concave up f of x. If it's negative, it's going to be decreasing f prime of x and a concave down f of x. And the reason why this works is because of the same thing as this. F double prime of x is the derivative of f prime of x. So if the derivative of f of x is positive, f of x is increasing. Similarly, if the derivative of f prime of x is positive, f prime of x is increasing. Same logic here. There's one more thing. When it's 0, I'm actually going to skip what happens to f prime of x because it's the same thing. There are two possible cases. So I'm not going to, I don't have space to write both cases right here, which is why I'm going to leave this alone. Same thing that happens here, though. Either case is going to be their maximum or minimum for f prime of x. And what happens to f of x is that there's something called a point of inflection. And the point of inflection, POI is its abbreviation, is basically when a curve changes from either concave up to concave down or concave down to concave up. It basically changes concavity. So that's basically a summary of curve analysis in a very small table. And obviously, since this is a final review, I'm not going to go too in depth into it. It's just refreshing the terms. We're actually almost done with chapter 3. I thought we might get cut off in the middle, but we can definitely finish chapter 3. And then our next video, we'll talk about chapter 4 and 5. Final two topics in chapter 3 are antiderivatives and differentiability. Antiderivatives are basically when you do the opposite of a derivative, you undo the derivative. And it's usually denoted with a capital F. So this capital F of x is going to be the antiderivative of f of x. How do they relate to each other? When you take the derivative of the antiderivative of f of x, you get f of x. Basically, it undoes each other. So this basically shows you have capital F of x is the antiderivative of f of x. Then you take the derivative of capital F of x and you get lowercase f of x, or the original function. Kind of similar to inverse functions, where if you do both operations, you end up with the original value. Antiderivatives, let's try to solve for some antiderivatives. Let's say we have 3x squared. How are we going to find the derivative of that? Well, you bring down the 2, you get 6, and then 2 minus 1 is just 1, so you have 6x. Now, how do you find the antiderivative of this? 3x squared. You do the opposite, basically. You take this and you move it up. I don't like to think of it that way, though. Let's start by adding 1 to the power, because we end with subtracting 1 here. So we start with adding 1 here. 2 plus 1 is 3, so we have 3. Now we still have the same coefficient, except in taking the derivative, we started by moving the power down. So what we're going to do here is we end by moving the power up-ish. What we're going to do is divide by this new power that we got after adding 1. We're going to divide by 3. And that's actually the reason why I chose this function rather than just x squared, because it simplifies. 3 and 3 cancel off, and we just get x cubed. And then you can take the derivative of x cubed to check whether or not we did it right. You bring down the 3, you get 3x, and then 3 minus 1 is 2. So 3x squared, which indeed is correct. What if you just have x squared, though? What's the antiderivative of x squared? You do the same thing. You add 1 to the power, so you get x cubed. And then the coefficient is still 1, but you divide by this new power, 3, and you get x cubed over 3. And you can't really simplify it because there's no 3x cubed. It's just x cubed to the power over 3. So that's as much as you can simplify. We're forgetting something, though, and that's plus c. For any general antiderivative that you take, you have to add plus c. The reason why is because when you take the derivative of a constant, you get 0. So even if you add x cubed plus 1, what's the derivative going to be? Derivative of this is 3x squared, we already found. Derivative of 1 is 0. So this derivative is still 3x squared, which is what we started off with. So we don't know what this constant is going to be. So we just add a plus c. So we can find out the constant later if we can. Like if we're given a point on the curve, then yes, we can find out the constant. If not, then no, we just leave it as plus c. Finally, differentiability. Differentiability is basically, does the derivative exist or not? There's 2 conditions. First of all, it's continuous at that point. And that has its own 3-step process. So you have to do that 3-step process before you prove continuity, and then only you can go on to the next step of differentiability, which is that the limit as x approaches c of f prime of x exists. Looks a bit complicated, but basically saying, if you take the derivative of the function and the limits of that derivative are not, the left and right are not equal, then it's not differentiable. Basically saying, at that point, the derivative is not continuous, meaning this function is not differentiable. Let me give you an example of that. Absolute value function is probably the most common example. Derivative of this side is going to be -1 since that's just the slope. Derivative of this side is going to be +1 since that's just the slope. The left and right sides are not equal, meaning it's not differentiable at x equals 0. This is what's called a cusp or sharp point. There are other types of cusps as well. This is a cusp. This is a cusp. Piecewise functions are especially not differentiable, but sometimes they are, and sometimes you have to prove how they are using these 2 conditions. So that's all of chapter 1, 2, and 3. That's a lot we just covered. So this video is probably going to be pretty long. But we talked about introduction to calculus with a review of pre-calculus. We talked about limits, area under the curve, and some basic things to know. And then we concluded with introduction to derivatives, basically. Some of the tools, some of the applications, and a little bit extra. But chapter 5 is where we're really going to go into a lot more derivative stuff, a lot more applications, and a lot more tools that we can use to find derivatives. So that's all we have for this video. Stay tuned for the second part, which is going to cover chapters 4 and 5, which is mostly just an introduction to integrals and more in-depth stuff with derivatives. So I'll see you next time. Good luck for finals.